now we continue with our exploration of non-abelian gauge theories, right? But before we go to deeper, more theoretical aspects of these theories, I want to use the Feynman rules we derived in the last few videos to calculate what happens at one loop level, right? We have already seen that if I put a few fermions and scalars transforming under a non-abelian theory, under some representation of the group, right, and plus gauge bosons, right, these theories will have only one coupling that controls all the interactions in these theories, and I want to see how this coupling runs, right, at least at one loop. So the idea is to calculate the running, and we will show this thing called asymptotic freedom, right? Which we discussed before, is when at high energies the theory, the coupling of the theory becomes smaller and smaller, so the theory becomes non-interacting asymptotically at high energies, right? But we'll prove that that happens for non-abelian gauge theories under some conditions, right? The conditions are important. In order to do that, we'll have to calculate all possible counter terms for this theory at one loop, right? And we start with the self-energy, right? Like we did with the photon. It is important thing to say is that this is a lot of algebra, right? A lot of these loop calculations. There are many more loops than in QED. We spend, I don't know, 5 or 6 videos doing carefully every loop in QED, right? And in the non-abelian case, there are more loops than in QED. I won't do all the algebra in detail, right? So I'll just show the main steps in the calculation and skip a lot of the algebra, right? You can go to my lecture notes for a much more detailed calculation, right? So I'll focus just on the new steps here and skip just brute calculation. Otherwise, you would be sitting there for hours just looking at me doing algebra, right? Of course, the lecture notes have a little bit of Portuguese, but the mathematics should be universal, right? So we start with the self-energy, and if you remember, in QED we had a very important property, which was the word identity, right? The word identity told me that this was 0, right? If I contract this self-energy, this full propagator for the gauge boson, and this is now my gauge boson independently of being abelian or non-abelian, right? In principle, I could draw the non-abelian ones in this way, right? But this is usually just used for the gluon, right? Even W's and Z's, people usually use this symbol, right? And I will draw so many diagrams that eventually these will become really ugly. The lazier I get, the uglier this becomes. So I better use the usual thing, right? So now this squiggly line right here means gauge boson, right? In this case, the photon, right? So in the non-abelian case, we know word identities are true, and that had an important consequence, right? Which was that the full propagator for the gauge boson could be written in a particular form, right? Which is this one. This was the most general thing you could write for a photon, right? So that condition fixes this Lorentz structure in front of the full propagator, right? We didn't prove this for the non-abelian gauge theories, right? We'll do that eventually, but you need to take a look at a generalization of the Ward-Takahashi identities, which is called the Slavnov-Taylor identities. And those I need to go into BRST, so that's for the future. It turns out that non-abelian gauge theories also obey this relation, right? But since I didn't prove it, I won't use it here, right? What we will do is calculate every contribution at one loop very carefully, right? And this will come out of the calculation as expected, right? If this is true, it should come out at one loop, two loops, right? So what we're doing here is just do the calculation, and what we will have shown with that is that this is satisfied at least at one loop. It's not a very general proof, but that's what we can do for now, right? So these are the diagrams that contribute at one loop to this full propagator, and I'll have to calculate all of them one by one, right? You could use your imagination here and come up with a few more one loop contributions. Specifically, you could wonder about these diagrams, right? They are all same order in the coupling, right? And in principle they should contribute. The thing is, these contributions are called tadpoles, name also attributed to Coleman, right? And these should be zero because they are proportional to the expectation value, um, the vacuum expectation value of the gauge field, right? And if this is different from zero, then I break a lot of symmetries spontaneously, right? Including Lorentz, right? So this, by Lorentz invariance, all these tadpoles should be zero. And that's why I'm not calculating them. Right? But you can also calculate them and show that the sum of these guys is zero, right? So now let's start with this guy, right? We'll start with this first guy. Let me just define a few things, right? Just to keep everyone's mind at ease, right? This is my symbol for the fermion. So for the sake of this calculation, I'm assuming there are fermions transforming under some representation of the gauge group, right? But I'll leave the number of fermions arbitrary, right? I can have more than one fermion, right? This is the gauge boson, as I said before, right? Now I'll be talking about a non-abelian gauge theory, so these are non-abelian gauge bosons, right? And this dashed line will be the Faddeev Popov ghosts, right? Also, as far as the perturbative expansion here, right? Remember that these couplings were proportional to G. So this is G square. Same here. But this 4 gauge boson vertex is itself proportional to G squared. So you see that even if I have just one vertex here, that's the same order as everything else. And the same is true here. These vertices, well, these vertices are all proportional to G with the exception of this one. And so it's all at the same order. So let's start with this guy. And let me paste it down here. Right? So this diagram is very similar to the one we calculated in QED, almost the same actually, because the gauge bosons, which are outside, they do not contribute to the loop, right? This is essentially just a loop of fermions, which I'll have to calculate. What is new then? The new part is that now in these two vertices, right, on the right and on the left, right, besides the usual gamma mu, the charge, which is now G, and all these factors which were already present in QED, now I have also the generators for the group. So on the right here, I have some TB matrix, right? B is the color of this gauge boson. And on the left, I have some TA color, right? And I have some indexes for the representation of the fermions, right? So these guys should have two indexes, let's call them A and B. And this other one is just A prime, B prime, right? Or something like that. But the propagator for the fermions now includes a Kronecker delta, right? So this guy could be a delta A prime, right? And this one a delta B prime or BA prime. It doesn't matter, right? What the consequence is that in the end you have really these primes going away, right? These indexes on the left, on the right will be contracted like that. And that's a trace in the space of these matrices, right? These will become, actually, if you do it carefully, right? Because one will be delta A prime and the other will be delta B prime B, right? The way this is contracted is in a loop, right? So you end up with something, if I manage to erase it, like that, right? If you do it carefully, which is a trace. So now you have a trace like that, right? Which in the space of everything else that is going around here commutes and goes to the front of the loop calculation. So you have essentially the QED loop times this new factor in front, right? So let me write that. I'll put the reference for the QED calculation if you don't remember in the description. But now I have this trace of TATB, right? Times the thing we already knew from QED. And in this case, right, since the calculation is exactly the same as we did in QED, it's obvious that you get that Lorentz structure dictated by the word identity of QED in this case, right? So Q squared G mu nu minus Q mu Q nu minus 8G squared, just replacing E by G. In QED you had the charge here, now it's G, right? Just because I'm changing the name of the coupling constant. And I did dimensional regularization over there. So I'm writing the result for dimensional regularization. Right? That's before we do the integration in the Feynman parameters. So that looks like this. It's a usual. This is the mass of the fermion running in the loop. And this is just the rest of the usual thing for the denominator, 2d over 2, right? I'm not worrying about factors of epsilon. I'm not worrying about many things here. We want just to take the rough pieces of this calculation, right? We don't want to worry too much about all the details. They are the same ones we had in QED. So if you have to solve them, it's the same solutions, right? Okay, so now what I want to do first is to figure out how much this is, right? We have seen in our review of Lie algebras that this can be written in terms of the normalization I choose for these generators in the representation I am in, right? So this will be, in our choice, delta AB times this coefficient CR, where R is the representation. For these guys, just in the case of SUN, which is our favorite one, right? If these fermions are in the fundamental, then Cn, which is the symbol I will use for the fundamental now, would be half. And if the fermions are in the adjoint representation, then Cg would be n, right? So the value of this constant depends on the representation for the fermions. Right? I will leave it like that, and we can specialize for particular representations in the end, right? Another thing to notice here is that I did dimensional regularization, but I didn't include our friend mu epsilon that compensates to keep the dimension of this coupling the right one, right? this, I could just put this right here, right? But I want, as to avoid, again, loading up the notation for everything. The main consequence of that is, for instance, if I do this integral, I'll get a log of some dimensional quantity, delta instead of delta over mu, right? But we know in the end I'll put some renormalization condition for this q square will become some q naught or some subtraction point, you know. We'll have some constant, some log of some constant in the end. I'll make that appear when needed. We know where it should be. All I have to do is keep track, right? This guy will generate a 2 over epsilon divergence. All I have to do is to keep track of where this divergent part here is. Because in the end, I know this will come together with the log of some arbitrary scale, which I'll use to write my Kalan-Zimanzik equation. So we can do this calculation in a very a much simpler way if we just look for the divergent parts of these loops and keep track of this guy. In the end, I'll bring back this log of m square, and that way I don't have to keep mu around. I don't have to be very careful about the finite parts of these integrals, right? That's much simpler thing to do, and it satisfies our aim here, which is in the end to calculate the beta function, right? The beta function will be calculated applying derivatives in this arbitrary scale on the counter terms, and the counter terms will only care about the divergent part. So that's the approach I'm taking now, right? That's why we were so careful before, so that we now can go a little faster, right? So now this is the loop I want to calculate. As I said, I want to keep the number of fermions arbitrary, right? So I'll sum over many of these loops. So now I want to know the sum over the number of fermions in my theory. So this is a parameter I'm defining now, right? Just tells me how many fermions I have. I will assume all of them transform under the same representation for simplicity, right? So if one of them is then in the fundamental, all of them are, right? So I have the same constant in front of all of these, right? And I'm summing now for all diagrams of this sort, right? And this will be starting from here, I q square g mu q mu q nu delta AB times. Now this, if I only care about the divergent part of this integral, right, I can take just the 2 over epsilon that comes from here, right, and do this integral, right? Just ignore this part, which would give me some, this would be some log of delta, right? Where delta is this, right? I would have to do that integral too, but if I only care about the divergent part, I can just take the gamma in the numerator and do this integral, which is just a factor of 1 over 6, right? And then this 1 over 6 cancels with this 8 here to give a 4 over 3, right? So I have here minus g square over 4 pi square. Again, there are logs of 4 pi, which I'm ignoring. I want to focus only on the diverging part. So this 4/3 is because this is 1/6, right? Number of fermions, this constant, CR, and then the 2 over epsilon, which is here, right? So again, keep in mind, this is not the full result, right? There are many more terms here that come especially from the integral of this part and all of that, but I'm really just focusing on the divergent part, right? The diverging part comes from this product of the 2 over epsilon that is here with the 1s, right? The expansion of this guy for the near 4 is something like 1 over 4 pi square plus other things proportional to epsilon. The expansion of this guy is just 1 plus this part. So if I multiply the 2 over epsilon that comes from here with this and this, I get this term that is written right here, right? And that's the diverging part. Okay, so now this is the result for my first loop. Let me put a box around this because we'll need it later. This one trivially has the desired structure for the self-energy, right? I say desired because there's an important thing that I forgot to say, right? If we have shown this for the photon, that because of this structure, when I sum over all contributions to the self-energy to the full propagator, right? I do this resum of all the 1 pi contributions, right? This structure implies that the photon does not get a mass perturbatively, right? This we know must be true for the gauge bosons too, right? They need to be massless, right? At all orders in the loop expansion, right? So that's why this is desirable, even if we didn't prove that the word Takahashi is true. Something like it should be true, right? So that's why I care about this structure. Now let's go to the next loop. And here we have loop number 2, right? This is genuinely new for non-abelian gauge theories, right? There was nothing like it in QED. So in blue here I define the momenta, right? Incoming Q, and I'm integrating over P for the loop, right? These green indexes indicate the color for the gauge boson, the adjoint representation index, right? If you don't want to call it color, and the Lorentz index for this gauge boson. So this notation, for instance, means that the polarization for this guy would be epsilon star nu of Q, for instance, right? And the color B means it contracts with the vertex here with index B, right? In the middle, you have the indexes for the propagator. So this propagator here will have a delta d prime and a G. This is our Lorentz indexes, right? So you have a G sigma prime, right? And the same is true here. And the one to the left is contracting with the vertex to the left, and the ones to the right are contracting with the vertex to the right. That means that these vertices will contain, of course, the coupling constant, but also some F, in this case, A, C, D, right? You remember this vertex for the 3 gauge boson interaction is quite complicated. Now you have these very messy combinations of G and some say mu nu, some momentum combination here, rho, and so on and so forth, right? You have some very complicated thing here that contracts these mu, sigma, and rho indexes, mu, sigma, and rho indexes in a very symmetric way with these 3 momenta that go into the vertex, right? Same is true on this side, but here I'll have G, F, B, C prime, D prime, right? B, C prime, D prime, right? And also this very complicated combination of these Lorentz indexes, right? Sigma prime, rho prime, and nu that is going on here, right? Well, with that in mind, with all these conventions, right, this choice for the indexes, I can write the Feynman rules, right? This is symmetric under the exchange of these 2 gauge boson, so there's a symmetry factor of 1/2. I'm integrating over P, right? That's the loop momentum, right? I have a propagator for the gauge bosons. If I ignore the deltas and the G's that I'll put further on, the propagator looks really just like a scalar, as long as I use the right gauge, right? And I'll be using the best one for that makes our calculations simpler, which is the Feynman-Tooth gauge. So I'm choosing psi to be 1, and then these propagators are just minus I white minus I over P square, and the other propagator is just minus I over P plus Q square. Again, I could have I epsilons here. I could try to fix the infrared divergences by putting a fictitious mass for these guys, right? All those things we did before. I'm not doing any of that here because I'm only after the UV divergent part, right? Then there's the G square because of the couplings, right? These two F's I can write here, F, A, C, D. Now start using these deltas that I didn't put here yet, so I can use this delta and this one to eliminate the primes from here. So this is F, B, C, D, right? And I have the product of these two very complicated Lorentz structures with G sigma sigma prime and G rho rho prime, right? That I'll call N mu nu. Should be obvious that only things that are left is mu and nu, which will be contracted with the external polarization. All the other Lorentz index should be summed over, and this is the how that thing looks like. Right, let me move it down just a little bit. Right, this is what this thing looks like. So the vertex to the left is here, right, depending on mu, sigma, and rho in a very symmetric way. All the momenta are here, right? Then there's this thing in the middle that comes from the propagator, it's just G sigma sigma prime and G rho rho prime. And then the vertex to the right, which depends on nu, rho prime, and sigma prime, right? There's a lot of contractions I can do here. I didn't do them yet, right? Before we move on with these numerators, again, these things get complicated because now you need to do Feynman parameterization, complete the squares in the denominator here, and that will be very complicated when you want to do in the numerator. So most of the algebra comes from trying to simplify this numerator. Right? One thing which this is more complicated than we did before, but it's not new, right? It's the same kind of manipulations you did when calculating loops before. What is new here is this F, ACD, BCD here. This we have seen is again dictated by this normalization for my representation, but these guys are automatically in the adjoint representation, right? This is the same as a product of two generators in the adjoint representation, and we have seen this before. This is just C2, right? The Casimir in the adjoint times delta AB, right? That was in the video for our Lie algebra review, right? And remember, the Casimir in the adjoint of SUN is just N, right? If I assume SUN, I won't for now, right? But I'll leave this thing going around, right? So now what we need to do, right? The next step would be to start doing all these manipulations we are used to. So Feynman parametrization, right? I just listed a few of the tricks here. So you do Feynman parametrization, you complete squares to get something like that, right? And then you have to do this change in this mass here, right? Exchange P for L everywhere here. Do all the contractions, all the integrals that are odd will be 0. The even integrals, there's this trick you can do, right? Just considering the Lorentz structure. And that will make, of course, as I said, I'm not doing all these calculations. That will turn the numerator into this, right? And then you do the integral, right? For L, right? You do the integral for L, and then this becomes this thing. So now you have the answer for the whole propagator, right? This is not very enlightening in itself, right? You have all these factors here that just come out of the calculation. There's not much in terms of interpretation we can take out from these factors. But the thing to pay attention here in this calculation is these structures in color here, right? You see that I have Q mu Q nu, here G mu nu Q square, also here G mu nu Q square, right? If I am to get this desirable Lorentz structure, right, I'll have to have the same factor in front of G mu nu Q square and Q mu Q nu, right, just with a sign difference between them. Right? But that's not here yet. You see, that's not the structure we get in yet. Specifically, here you see that the gamma, always I'm trying to get the divergent part, but here I have to be careful because the gamma here has more poles than this gamma here, right? If you remember, this guy, it has poles for d equal 4, but also in d equal 2, which, if you remember, is a signature that this guy has both, if I would speak in terms of a cutoff, right? This diverges both as the cutoff square and as a log of the cutoff, right? It has both quadratic and logarithmic divergences here. While these guys, which appear both here and here, right? They only have poles in d equal 4, right? Which indicates to me that this is the equivalent of a log divergence, right? We have seen this before, right? And another consequence of the right Lorentz structure, right? If I have this thing be proportional to G mu nu Q square minus Q mu Q nu times a function of Q square, right? Is that for all the same reasons that we had for QED, this guy only contains logarithmic divergences, right? Because of the powers, right? You just have to do the power counting here, and you see this guy is logarithmic divergent, right? As a consequence of this structure. So this quadratic divergence needs to go away at the same time that I get the right Lorentz structure. The fact that I'm getting 3 different structures here already tell me that this diagram cannot do it alone. Of course, this structure does not need to be true on a diagram per diagram basis, only on the sum of all the diagrams. So that's a sign that if this works, it will be because when I add all the other diagrams, this gets fixed, right? So we'll see. We have to go to the next diagram. Again, I'm defining the momenta in blue here, right? In this case, I have just the loop momenta running here and Q going straight through, right? In green, I have the color indexes, right? And the Lorentz indexes, mu, sigma, rho, and nu, right? And this is what I get for these 4 gauge boson vertex. Again, this thing is a very complicated expression that contracts all the 4 colors going in and all the 4 Lorentz indexes going in, which I'll write pretty soon. So let's try to write the Feynman rules for this guy. Again, I have a symmetry factor for this loop here. That's factor half. I have the integral over the loop momentum, 2 pi to the fourth, right? And I'll write the propagator for this guy, again in the same gauge, right? Feynman tooth. So I have a G sigma rho. I have a 1 over p squared for the momentum going around this loop. A delta for the colors, delta CD, right? And I have this coupling minus IG squared, right? Times this big thing, which I have saved right here, right? This is straight out the Feynman rule for this vertex with this choice of indexes. Okay? Now, this can be a little bit simplified. That's again our numerator, right? Now the denominator is really simple, but soon we'll complicate it, right? But for now it's simple, right? I can take this delta here and contract in here, right? Exchanging D for C, right? In the case, so I'm actually applying this guy down here. When I do that, in this case, I get FCC, see? And since F is anti-symmetric, right? This term will be 0 for that contraction. In the other cases, I just replace. Let me allow changes in this guy. So I just replace D for C here and D for C over there, right? That changes my expression in this way. And now I have CE, right? CE here. In both cases, these are summed, right? Repeated indexes are summed. So again, I get these trace over the generators in the adjoint representation, right? Which we have seen before. So this is just the Casimir in the adjoint representation times delta AB, and the same here. So C2G delta AB. So you see the color structure is the same in these two surviving pieces. This is 0, right? This goes away. So these two surviving pieces have the same color structure, which I can bring out. And now I have to deal with the Lorentz one, right? So take this guy, for instance, right? I'll have this times G sigma rho here. And the same thing, and then this part times G sigma rho. In both cases, I have a very similar situation. This first part is the same. And the second one, when I contract G sigma rho, this piece here becomes just G mu. And this piece here is G sigma rho times G sigma rho, which is just count the number of space-time dimensions, right? This will become D, right? And the same here, right? Exactly same situation here. So this becomes just 2G mu times D for the first piece, and just minus G mu for the second piece, and there's a factor of 2 because of these two terms, right? These can be straight out put here, right? Just have to take the G out, and I get a pretty simple expression for that loop number 3 that we are calculating now, right? It's just G squared, this color part here, right? 1 over p squared, G mu and d minus 1, which is here, right? This is g mu d minus 1. So this one is the simplest of all these loops, right? But since there we can have nice things, now we'll complicate it, right? And the reason is that in dimensional regularization, right, we have calculated a loop really similar to this one when calculating lambda phi 4, right? It's very similar. Other than these factors and g mu here, the integral is exactly the same, right? I have just a p going here, right? And I'll have a d for p integrating over 1 over p squared. Everything else goes out of the integral, right? And we have seen that this integral has both a quadratic and a log divergence, right? But the log divergence, just by dimensional analysis, will be proportional to m squared, the mass of the particle going around that loop, right? That means if the particle is massless, in the case of lambda phi 4, this particle had a mass, so I get this log divergence. In the case of a massless particle, which is what we are attacking now, right? The log part is 0, right? That means that if I do dimensional regularization for this guy and take d near 4, this loop will be 0, which is fine, right? But if I do that right now, I get no information about the quadratic part that comes from when I take these two dimensions, right? And then I will never know if the quadratic divergence here will cancel that quadratic divergence that I had before in loop number 2, right? In this loop. Right? So I want to use some approach here that allows me to prove that the quadratic term coming from this guy will cancel the one coming from that guy, and actually get me the right Lorentz structure and just a log divergence, right? If I just take these to 4 dimensions, I'll lose that information. I'll never know. I can assume that is true, but then I'm enforcing. That would be the thing to do if I already knew that this is true, right? Because then I know they need to cancel, right? I don't want to do that right now, so I'll have to do something a little bit more complicated. One trick I can use is now to take this expression and multiply this to get the same denominator I had in loop number 2 above, right? Remember, loop number 2 had the product of 1 over p squared by 1 over qp squared, right? That was the denominator for the previous loop, right? If I now take this one and just multiply by this, I'm doing nothing in terms of the just multiplying by 1, right? But now I have to do Feynman parameterization and all the same procedure before, take care of this numerator, and I'll have a structure really similar to loop number 2, right? And then I will be able to compare and see if the quadratic part and the log divergence are really canceling each other, right? If I do that and now we start doing the integral in d4p, right, with all the same tricks, then I'll get this very complicated expression, right? Because I like to complicate my life. But now I can find these same 2 structures that I found in previous loop. In fact, on the previous one, I had 3 such structures, right? I had also a q mu, q nu structure, which is not even appearing here, which is a bad sign. Shows us that just this loop won't be enough either, right? We'll need more loops. Now what I want to do is make a sum of diagrams 2 and 3, right? This is loop 3 and I have loop 2 above, right? To see what happens to each of these structures when I sum these two loops. So here I have the term that multiplies each of those three structures when I add up diagrams 2 and diagrams and the loop 2 and loop 3, right? So for instance, this part right here, right? You can recognize this from here. You see this part is exactly what I have here with the sign up there, right? And this is what is multiplying these structures. I already wrote both loops so that the integral and these things in front are the same in both, so I can compare just these factors here. You see this one is here too, right, with the right sign. And the rest is coming from the previous loop, loops number 2. So what I would like at this point is for these two factors to be just different by a sign, right? One should be minus the other. This is not true, right? You can try to do some algebra here, but that's not true. These are not equal, right? And this one should be 0, right? Because this is the part that contains a quadratic divergence, right? And none of these is true so far, and that means I still have to add more loops before I can have the right structure, right? Keep in mind that I'm not talking about diagram 1, right? Loop 1, because loop 1 has the right structure, right? On its own. So what I have, what can I do about this now? Go to the next loop, right? Which is number 4, and I have it right here. So now I have to do the loop involving the ghosts. The ghosts are much easier, right? It's just scalar propagator, right? With the added extra color, right? So this guy is now proportional to a delta d prime, right? The ghosts have the same, they are also transforming in the adjoint representation, so they have the same color indexes as the gauge bosons. And of course, this is the usual thing, right? And here I have the Feynman rule for the vertex involving gauge, ghost, ghost, right? Again, coupling G, some F of the three colors going to the left here, A, DAC, right? Same thing here, right? C prime, B, D prime. And of course, these vertices, they depend on the momenta going out. So the one on the left is Q plus P mu, and the one on the right is just P nu because of these indexes here, right? So now I can write the Feynman rule for this diagram, right? Remember, this is a loop of something that is anti-commuting, so it works like a Fermion loop, right? You have an overall -1. That's the strange part about ghost loops, right? And now I have just the integral over the momenta in the loop, the propagators for these guys, which just look like scalar propagators for a massless scalar. So again, in this case, I have the same denominator that I got for the other one, so it'll be easy to compare everything. And I have the product of these two Feynman rules. I just get a G square F D A C F C prime B D prime. Have the deltas for the two ghost propagators, C prime, delta D prime, and then some momenta in my numerator here, which will make the calculation a little bit harder. Again, I have to do Feynman parametrization, complete squares, and change this numerator accordingly, right? As I said, I'm not doing all these calculations. If you do them carefully, this is what you will get for the ghost loop, right? So now you see I have same thing in front, right? I did it on purpose. Now this part is exactly the same as for loops 2 and 3, right? And I have again these same structures. Now in the case of the ghost, I have this structure that has appeared in all the 3 loops, right? 2, 3, and 4. But now instead of having g mu q squared times gamma of 2 minus d over 2, I have q mu q nu, which didn't appear in the previous one, right? And so the only guy that has all the 3 structures is was loop number 2. So now what I have to do is add these factors to the ones I had before and see what happens. We start with the first structure in blue here. So this is what we get if we add this new contribution to what we had before. So it is the sum of loops 2, 3, and 4, right? Just do some algebra and you get to that. And this is very important because now, if you remember properties of gamma functions, we know that 1 minus d over 2 times the gamma of 1 minus d over 2 is gamma of 2 minus d over 2, which means that now this structure, right, is actually just the other one, the green one that does not appear here, right? I actually just have to multiply these over in the gamma, and then this becomes this thing, right? The other 3 multipliers here, multiplying the green structure. And that means that now I have nothing proportional to this gamma anymore, right? This thing just removed the pole in d equal 2, which means we have no more quadratic divergences here, which is one of the things that should happen if the Lorentz structure for these non-abelian gauge bosons is the same as we had for the photon. So now when we go to the other function, right, this one, we have to add this extra piece, right? This has become the same as this structure here, right? Also, the red one here, which is the same gamma function times q mu q nu, got a new contribution from the ghost propagator, so I have to add it. And then again, I have to do some algebra, and I get this expression right here. Now, the quadratic divergence is solved. I don't have to worry about this structure anymore. I just have these 2. But they need to be the same minus a sign, right? They should differ only by a sign. Now, this is not obvious here, but the thing is, this is inside an integral in the Feynman parameter, right? And I have some freedom with that integral because, you see, I'm integrating the dx. The dx is missing here from 0 to 1, right? And I could easily make this change x going into 1 minus x, right? And this thing in the denominator, the delta here, is symmetric under that, right? If I make x go to 1 minus x, nothing changes here, right? I compensate the sign of the change by flipping the integral after I do the change, right? So this is really symmetric under this change, and I can take any of these pieces here and make these x go to 1 minus x freely, right? With that freedom, it's no wonder that these 2 things didn't come out the same from the start. I have to do some changes to prove they are the same, right? In particular, you see I could take x, right, as x over 2 plus x over 2 and make that change in one of these two pieces. And that is the same as substituting x per 1/2, right? I just took the second part, made a change here, and added up again. So if I find any linear term in x on these big polynomials here, I can just exchange x by a number, by 1/2. And that's very powerful in simplifying this expression. This is already really simple, so I'll try that on the first one, right? The first step would be to just distribute all the multiplications here and get a explicit polynomial in x, because then I can use these in the linear term in x, right? And that's what I did here, right? So if I just take this expression, right? Can you see everything? Yeah. So I can take just this first expression and write explicitly as a polynomial in x. I can take this piece and do this change in the integration variable to replace x by 1/2, right? Now, this whole piece here, just this part, becomes this, right? Once I do that replacement, right? And now I can take this 1 minus d over 2, right? And write it in this way, right? Just bring it to the front and see what polynomial I have, right? This 4x squared minus 4x plus 1, right? Which is exactly this thing right here, you see? So I managed to write this in exactly the way I wanted. Now, this structure and this one are exactly the same minus one sign, right? Which is what I wanted. So I got now, I managed to show at one loop that the sum of diagrams 2, 3, and 4 satisfy that Lorentz structure. Loop 1 also has the appropriate Lorentz structure, and that means that the whole, I only had these 4 loops, and that means that the whole self-energy has the appropriate Lorentz structure. Now we can move on to think about the beta function and see what else we need to calculate, right? So as I renormalize this theory, I'll have to introduce these 3 counter terms, right? You just have to do the power countings and see which diagrams are divergent, but that will be exactly the same power counting as we did for QED, so I'm not doing that again. And you'll find out that you have these 3 counter terms to introduce, right? Then if you write the Kalan-Zimanzik equation, again, following the same logic we did, for instance, for the scalar field, right? This is in previous videos. You can find out these leading order expressions for the gamma functions, right? Which of course depend on the corrections to the propagator of the fermion in this case. So this is the gamma function for fermions, and on the propagator for the gauge boson for this one. So this is the gamma function for the gauge field. And combining those two with an analysis for the Kalan-Zimanzik equation for the 3-point function, you can find the leading order contribution to the beta function, right? You find out that this starts at order g cubed, right? And that is done in detail in page 210 of the lecture notes. I won't do it again here. And you see it's a very similar thing to what we get in QED, with one important exception, that in QED delta 2 was equal to delta 1. So these two would cancel out and you only get a dependence on delta 3. Now things are more complicated and I'll have to calculate each of these counter terms separately. Okay? Now, delta 3, I already have all the loops I need to calculate, right? Delta 3 is this counter term, so this piece need to cancel the divergent part of the self-energy, right? And I already calculated the contributions to the self-energy. So let's start by getting delta 3, right? This guy needs to cancel the contributions of all these diagrams. I have these 3 for the gauge, the pure gauge part of my theory, right? And a number of diagrams like that, one for each fermion that interacts with my gauge boson, right? That transforms under some representation. And the representation information is here, right? With this gauge boson, right? So now, delta 3 will be then. You see a lot of common factors there, right? It needs to get this divergent piece, but this is common to both. Right? This is also common to both, right? But the different part is right here, here and here. This is positive, right? You see these two negative signs cancel each other. So let me write it like this. I'll just put a g square over 4 pi square here. Notice this structure I don't need to worry about because that's explicitly included in the Feynman rule for the counter term, right? So this guy here needs to be equal to the same thing multiplying that over there. Even the sign is already there to provide for the cancellation. Right? So I can bring a g square over 4 pi square out here. Actually, it's 4 pi square, 4 pi square. Yeah. And this term is just a 5/3 of C2G. Remember, this is not gauge independent, so this is in the Feynman-Tooth gauge, right? We can always generalize if we want, right? And this is 4/3, right? This piece here, there's a minus, so 4/3 of the number of fermions times this constant for the representation. And then you have the divergent part, right? This will provide the divergence. And of course, when I fix, when I do my renormalization conditions, I will introduce some arbitrary scale, right? The way this looks, if I did the expansion for d close to 4, is that I would have a 2 over epsilon, and then depending on the my renormalization scheme, right? I could have the log of the subtraction point here. I could have, right? But in the scheme we have been using, right? I just want something like that for in the counter term, plus terms that are independent on m square, right? And order epsilon, right? Which all go away as I go to 4 dimensions, right? So whatever I include here in the counter term or not depend on the scheme, but it doesn't matter because I just want to use this to calculate the beta function, and then the derivative in m will eliminate everything but this, right? So I only have to put m square to the power d, actually 2 minus d over 2, that I'll get an expansion for d near 4, right? As I go to d equal 4, that is exactly this one, right? So I don't care about the other finite or m square independent terms that might appear. That implements the kind of scheme I want to use. So now I got the counter term delta 3. I also need to get my beta function delta 2 and delta 1. So let's move to delta 2. So Delta 2, as can be seen up here, eliminates the divergences on the fermion self-energy, right? So at one loop, that means I have to calculate this diagram right here. And the only new thing here is to remember that this fermion now carries some index of the representation which it is in, right? So there's this, usually I'm using capital indexes to indicate these, right? So there is a color coming here, but it shouldn't change, right? It's not the same as the colors for the gauge bosons. It's the color, usually the fundamental representation for the fermions, right? But that will come out naturally here. Why? Because as you look at this vertex and this one, right, and the gauge propagator here, you have some TA here, some TB here, but a delta AB on the propagator. And that leads to these two terms here. You see already, instead of writing TB here, I wrote TA because of the delta here. Same with the Lorentz indexes. So now see what happens with these two matrices, right? We have seen that if you contract, right, you make this product TA, we normalized the representation so that this is equal to C2 of R times the identity. And this identity is carrying these A, B indexes. So you see the color does not change as it go through here, right? Now, I need to do this integral, right? Since I'm only interested in the divergent part, I can even disregard these masses here. So if you want to do this calculation, you can even disregard the mass. You have to use the usual relations, right? You can contract this Dirac matrix with this one and eliminate the p slash here, but you get some factors of 2 minus d. Remember, we are in dimensional regularization, you have to be careful. So, but that's all similar to what you did before, right? So if you do all of these, you get the following expression for the divergent part of this diagram. Right? It will be a IG square over 4 pi square K slash, this K slash right here, C2 of R gamma of 2 minus d over 2. See, I can be more careless now with taking the divergent part because I don't need to worry, since there's only one diagram here, I don't need to worry about cancellations in quadratic divergences or nothing like that. There's only a logarithmic divergence here, and that's the only diagram, so I can straight away take P to be very big, right? And now with this, I can get the counter term, right? I need this thing at some scheme, right? At some arbitrary scale to cancel each other, and that immediately fixes delta 2 to be this guy, right? There's an I explicitly in front of this, so I don't need that I. This will be just minus g square over 4 pi square. Again, I'll do the implementation of my scheme the same way I did before. Just put a m square 2 minus d over 2 here, right? That will lead to 2 over epsilon plus the log of 1 over m squared plus a bunch of terms, and this is the only thing that matters, right? In this scheme, I can do it like that. And then C2 of R. Now we can move to the calculation of delta 1, right? Which is the counter term for the vertex, right? And these are the two one loop contributions to the 3-point function, right? To the vertex itself. Let's start by calculating the one in the left, so diagram A. Here I defined all the momenta in the most convenient way, and these, again, I always have to define the indexes that are going to be contracted on the vertices. I have to follow these to write the Feynman rule. I have to follow this line backwards, right? And that tells me in which order the matrices that are here will appear. So that's why I have TC, which is the first one. So C is going to the right here. TA, which comes from here. And then TB, which is the left one here. TC, TA, TB. Right? I can commute these matrices with the Fermion propagators because the Fermion propagators are diagonal in this space, right? These guys are contracted like that, A, B, B, C, C, D, right? Because the fermion that was in the middle here was a delta in that space, right? So I can actually factor those guys out. And that also tells me, following that line backwards, also tells me the order of the product in the spinor space. So this is Dirac matrix alpha here, right? Alpha is to the right. Then this propagator, then gamma mu, which is contracted with this one. Then P slash plus K slash. Then gamma nu here. Of course, this propagator, which I only have written here, right, has a delta BC, so I can replace this by B, right? And a G nu alpha, which allows me to change this alpha into a nu here, right? And all the factors of I and all the other things that come from these propagators, I already took into account. You see the coupling is here is G cubed because I have 3 vertices. Now, what is new in terms of tricks for calculating this loop? This part is the usual deal, right? But this one is kind of new. There's a nice trick for calculating this product of generators, right? So let's take a look. That's TB, TA, TB. B is contracted, right? And the way to go about this is to first commute 2 of these guys, to write TB, TB, which we'll know a expression for. But of course, then I need to compensate, right? I cannot just commute that. I have to add the commutator. Sorry, TB to the left, TA, TB. Now we know this guy is just C2R times the identity, which I multiply here. And this guy is the algebra of the group. It's just F, A, B, C, T, C. But we can go further, right? This is, so, C2R TA plus I, F, A, B, C, T, B, T, C. Right? Now, the trick here is to symmetrize this, right? So I'll just write this guy as half of itself twice. So this plus the same. But on the second one, I can exchange B for C. I get a minus here, right? But then I rename the indexes, right? So I rename C B and BC. So this turns back to BC, but here I get CB, which allowed me to write this as half of FABC commutator TB TC, which again is the algebra, so I got this product of twice the structure constant, A, B, C, I, F, in this case B, C, D, T, D. Right? Now I can use this here and continue my calculation. So I have C2R TA minus, there's an I here, an I there, that's where this minus comes from, minus 1/2 F ABC, F BCD, TD, right? But now this product of two F's, you see I have BC here, I have BC there. Cyclically I can bring this D to the front. And then I have something we used a few times already. This is the trace in the adjoint representation. So this is the Casimir delta AD. Right? So I managed to write this product of three generators in terms of Casimirs. One Casimir for the representation of the fermions and one for the adjoint. And this is all multiplying TA, because of course this has a structure of has indexes of a generator, right? It's the vertex for this interaction. If I go back with this to this expression, then I can remove the color factor, which is this, out of the integral. Right? The integral itself, since I'm now, again, not worried about complicated cancellations, this is already log divergence, right? I can completely ignore this case here, just take the limit of P going to infinity and actually calculate just, right, this G cube, this part, C2R minus C2G TA times this simple integral, which gives me the most the diverging part of that diagram, just gamma nu P slash gamma mu P slash gamma nu over P square cubed. And this is, let me copy the diagram up here. This will be just I G cubed over 4 pi square C2R minus half C2G TA gamma mu. Again, same thing, right? The log divergence plus finite terms, which I don't care too much at this point. So this is diagram A. So let's move on to diagram B, which is here. Again, I'm doing the same kind of conventions here. These colors indicate which indexes are contracted on each of these vertices, right? And in the case of this triple one, all the indexes that will be carried into it. I already used all the G minus that comes from the propagators and also the deltas in the adjoint index, right? So you see nu is already from, for instance, this vertex is already contracted with nu in the complicated three boson vertex over there. Right? Now, the color structure is again the new thing, right? I can bring this over here to contract with these two matrices, right? And get FABC times TBTC, right? Which again we can do the same trick we saw before, right? This is an anti-symmetric matrix, so you can get the anti-symmetric part here just by symmetrizing. You just add half of it with half of it, you get just I over 2 over times C2G TA, right? So I can make a commutator appear here because only the anti-symmetric part of this object survives, right? So I can use this here, right? And again, I can just disregard everything in comparison to P. So I can take P to be much bigger than K prime, than K, and there's another one, K and Q, right? K prime and Q, right? And then this simplifies a lot, and you can actually get the diverging part of this diagram quite easily doing that instead of calculating the whole thing, which could be a lot of algebra, right? If you want to practice this kind of thing, then you can go for it, right? So the diverging part will be IG cube over 4 pi square times 3/2 of C2G TA gamma mu times gamma 2 minus T over 2 plus finite parts, right? And I only interested in the divergent part because I want to find out the counter term. Right? So this is diagram B. Now we can combine diagrams A and B to get the counter term for the delta 1 counter term, right? So just so we can remember, I repeated diagram A down here. This is just A, right? And we need these two to have their divergent part concealed by the counter term at some scale, right? You can see they are very similar. These things are the same, right? I have these 3/2 of C2G here, which will be concealed partially by this minus half. So you have just C2G, right? 2 over 2 C2G positive. So, and the rest is the same, right? So you see the counter term will contain C2R plus C2G because of that. C2R coming from here and C2G coming from this combination of both. Right? And again, I'm doing this scheme implemented by this m square in the denominator here. That gives me delta 1, which was the last missing counter term that I needed. So now I can go forward and calculate the beta function. Right? As we have seen before, the beta function for the only coupling in this theory, which I call G, is given by G m del m of this combination of the counter terms minus delta 1 plus delta 2 plus half of delta 3. And now I just have to write all these guys here, right? It's important to remember that in all of them, I have these gamma of 2 minus d over 2 over m squared to the power d minus 2 minus d minus 2 over 2, right? And I want, in all cases, I'll apply these m del del m, right? This is this near 4 dimensions, right? This is just 2 over epsilon times the log plus the log of 1 over m squared plus a bunch of other stuff that do not depend on m squared. Even 2 over epsilon does not depend on m squared. So both of these go away, right? The derivative only acts on this guy, right? Which gives me minus 2 over m. And then the m cancels with this guy. So this is just minus 2, right? I can already apply this derivative just exchanging this thing by minus 2 everywhere. And so I'll put a minus 2 over here, g. And now I just write all these pieces, right? So for instance, for delta 1, I'll just ignore this part and put the rest in here. Let me make these a little smaller to give me space. And then let's write everything. So then I'll start with minus delta 1, just copying what's over there. So g squared over 4 pi square C2R plus C2G. Now the piece coming from delta 2, right, is just minus g squared, as we calculated before, right? 4 pi square C2R. This is the contribution of the self-energy of the fermions. Right? And now the term for the self-energy of the photon is g squared 4 pi square 5/3 of C2G minus 4/3 of number of fermions CR. Right? Now I just bring all these common factors in front, as I have said at the start. The beta function starts at order g cubed, as you can see here, right? And then I just add whatever is left to get a beta function finally, which is minus g cubed over 4 pi square times 11/3 of C2G minus 4/3 the number of fermions CR. Right? It's important to say that we did everything in the Feynman-Tooth gauge, right? But at this point, all the gauge dependencies would have concealed, right? The beta function itself is not gauge dependent at one loop. Right? So now you see, now it's where we actually have fun with these, right? So you can see that on one side, I have the contribution coming from the gauge bosons, right? Just the gauge interactions. And on another side, the contribution coming from the fermionic part, right? It should be clear that if I have no fermions, then the beta function is negative, right? This is especially clear if I substitute for SUN here, but you can already see that, right? The condition, in fact, in this case, would be that the number of fermions times this constant that depends on the normalization, the representation should be smaller than 11/4 of the Casimir operator for the group, which depends, of course, on the particular group. Now, if you take SUN, then C2G is just N. And if you take our fermions in the fundamental, right, let's put psi is in the fundamental representation, then Cn is 1/2. In that case, this condition becomes that the number of fermions should be smaller than 11/2 of the number of colors. The number, I mean, the size of the group, right? So, the number of generators of SUN. So you see, the fermions are forcing the beta function up, the gauge bosons are forcing the beta function down, right? It's no wonder that in the case of QED, right, you had a Landau pole, because in there's no self-gauge interactions, only the fermions, so the beta function was positive and the coupling grows as I go to high energies. Now I have these two opposing forces, right? And the most famous case in nature, right, that was actually realized in nature of this thing is QCD, right? In the case of QCD, the gauge bosons end up winning, right? Because N is equal 3, and the number of fermions is 6, right? Up, down, charm, strange, top and bottom, right? Which is below this condition, right? So I put a 3 here, I see that this is safely below 32/2, right? And that's a very important point, right? It's a Nobel Prize, actually, which is was for the proof that QCD they had this asymptotic freedom. So it made sense of to speak of free quarks. At least if you look quarks at very high energies, they behave like free particles in that limit, right? Another important thing that we can take from this is that if you have no fermions, like a pure gauge theory, then you always have asymptotic freedom. So all non-abelian gauge theories, or pure Young-Mills kind of theories, will have asymptotic freedom because the beta function will be negative. Right? So that's it for this video. Thank you.